It's all just fodder for discussion. We're not going to be summarizing them or keywordizing them or normalizing them in any way. So it's just for us to have something to discuss. All right, with that, it is my pleasure to introduce our next speaker, Dr. Dean Tantillo. Dr. Tantillo, he's a professor in applied theoretical chemistry, he's a professor in chemistry here. He did a postdoc in applied theoretical chemistry at Cornell, after which he very sensibly decided to come to a much warmer place in the country back in 2003. So you've been here for about 20 years now.
20th year, yeah.
Wow. Professor Tantillo's research investigates the structures and reactivity of organic molecules. He's a world leader in mechanistic organic chemistry. In particular, his research is focused on applying the tools of theoretical chemistry to, quote, construct new models of reactivity that can be used to both rationalize and predict the origins of reactivity and selectivity for organic, organometallic, and biosynthetic reactions. He's recognized as a world leader in the physical organic chemistry community and is regularly invited to speak at top physical organic chemistry meetings. He is also arguably the world's expert in applying quantum calculations to natural products chemistry. He's also an outstanding educator, recognized by both the UC Davis Academic Senate Award for graduate and professional contributions in 2016, very nice, and for his efforts in undergraduate teaching in 2011. He's been a constant advocate, educator, and mentor to minoritized communities in STEM fields. And I think he's going to talk about the next 2 paragraphs of introduction in his talk on making chemistry accessible to visually impaired students. So I will leave that to him. Thanks for coming. We're really looking forward to the talk.
Okay, thanks for having me. Thanks for the intro. As you can tell from the intro, this talk's going to be different. I'm going to try to teach you some chemistry. So buckle in.
Nobody leave.
Yep, lock the doors. So I am a chemist. Okay, so that should probably cause you to get some images in your mind. If you Google, as I did yesterday, the word chemist in an image search, this is what you get. This is a horrible picture for so many reasons, okay? I've never met a chemist who did that. So what my goal is today is to try to show you what a different image of what a chemist can be, several different images of what a chemist can be. And hopefully you'll leave here thinking that chemists don't look like that. All right. So I want to start by acknowledging that I am in the most privileged group in our country. Okay, pretty much by any criteria you can imagine. And so everything I say is filtered through that experience, but it's coupled with a commitment to self-reflection and lifelong learning. So I want you to take that as you will. As we go forward. Okay, so I'm not just a chemist, I'm an applied theoretical organic chemist. So if anyone here has taken chemistry and you heard organic chemist, you probably have the same reaction that every doctor I've ever gone to has had. So this is what usually happens to me when I go to a doctor's office. They say, oh, what do you do? I'm like, oh, I'm a teacher. They say, well, what do you teach? I say, chemistry. They say, oh, what kind of chemistry? I say, organic chemistry. And what do they say? Oh, I hated that. And I have a stock response. Well, you didn't take it from me. Okay. And I'm not sure why that is. Well, I think I know why that is. It's because of the way it's often taught, which is a lot of memorization, and it's set up to be a gatekeeping class and so forth. And it doesn't have to be that way. I'm going to try to convey a little bit of why I think organic chemistry is beautiful and how it should be available as a field of study to anyone, because there have been some traditional barriers preventing that. So to do that, I'm going to teach you a little bit of chemistry, and you're a captive audience, so here we go. So basically what I do, the kind of chemistry I do, which is applied theoretical chemistry, means that we use computers to do the math of physics to predict what molecules look like and how they behave. Okay, so I want to know what the structure of molecules are and what they will do. And that is predictable using good physics. And there's really two flavors of physics that we use, and I'm going to explain those to you briefly. The first is based on classical mechanics or classical physics, and this is really the idea. There's some equations, okay? This is really the idea of treating a molecule like balls on springs. The atoms are connected by springs that represent their bonds. So you don't have to worry about the math. This picture kind of covers most of it. So if you imagine that the horizontal axis in this plot is some sort of structure, some sort of geometric change, okay? And the vertical axis is energy. So this plot says that for some feature of a molecule, let's say the distance between two atoms, okay, there is an ideal distance. So for a carbon-carbon bond, there's an ideal distance. For a certain type of carbon-carbon bond, the most common one, that is 1.53 angstroms. It doesn't matter to me if you know that number, but there's some ideal distance. And this plot says that if I squish that bond shorter, there's an energy penalty. The red curve says the energy goes up. And if I stretch it longer, there's an energy penalty. The energy goes up. Okay? This is a simple harmonic potential. Okay? It's just a parabola. Okay? This is just like a spring. And how steep this potential is, how severe the penalty is for deviating from the ideal, corresponds to how tight the spring is. Is it a really loose spring or is it a really tight spring? If it's a really tight spring, you can't distort it very much without paying an energy price. If it's really loose, you can change it a lot without paying a lot of energy. That's all this says. And you have other equations for different features of molecules that might have different forms, but basically you can describe all the important structural features of a molecule with equations like this, and you put them all together into what's called a force field, which sounds like sci-fi, but it's not. Okay? And so this is one way that someone like me can figure out what the structure of a molecule is. We can vary the positions of all the atoms in the molecule to try to minimize the energy penalties and maximize the energy goodness. All right? And this is done a lot for conformational searching, which is basically figuring out the best shape of a molecule. This is done also for something called automated docking. That's if you want to take a small molecule and figure out how it fits into a big molecule, like a drug molecule binding to its protein target, for example. Okay? So that's all classical mechanics. When you do this kind of calculation, what goes in? Well, you give the computer the force field, which is filled with parameters, and you give it the atomic coordinates that you guess at. What do I think the molecule will look like, which is where I think all the nuclei are. And then the computer will vary those and get you an ideal version. Okay? The parameters are how steep the potential is, how tight the springs are, for example, and what are the ideal distances. Those parameters come from years and years of experimental data or the other type of calculations I'm going to tell you about. These calculations are super fast. What you get out are new atomic coordinates of the adjusted structure that's better, and an energy that goes with it. Okay? You already know a lot of computational chemistry. Okay, the problem with this kind of calculation is that it's completely dependent on the parameters. So if the force field has not been parameterized for the kind of molecule to which you apply the force field, then you can't trust the answer. That's a problem. So to get around that, there's a second type of calculations that uses a different subset of physics, which are called quantum chemical or quantum mechanical calculations. So this equation is a famous equation. This is Schrodinger's equation in its least threatening form. I could make it much more threatening. Okay? Even if you don't want to hear that, just read the little cartoon. Okay? So this comes from the recognition that electrons are so small that we can't just treat them as particles, we should also treat them as waves. And in doing so, that comes with some uncertainty about their positions. Right? So to do quantum mechanics, it sounds like a daunting thing, but doing quantum mechanics just means figuring out where the electrons are likely to be around a given set of atomic nuclei. And so to do this on a computer, what you do is you give the computer your guess at where the nuclei are, and then you give it something called a basis set, a set of atomic orbitals. So if you took general chemistry, these are s and p and d orbitals. If you didn't, all those orbitals are mathematical functions that are related to the probability of where the electrons are. You don't know exactly where the electrons are, but they have probabilities of being at certain positions. And those functions are centered on the atoms. For every carbon atom, there's a probability of where the electrons will be, for every oxygen atom and so forth. And then what the computer will do is it'll combine them, so it'll make linear combinations of those atomic orbitals to get molecular orbitals. So in other words, it'll take the mathematical functions you gave it, which are atom-centered, and it will delocalize them over the home molecule to figure out where the electrons are likely to be in the home molecule. And all those molecular orbitals together make up psi, which is the famous wave function. And the wave function, the square of the wave function roughly, is the probability of where all the electrons are likely to be. So all the Schrodinger equation does is it takes the wave function and it operates what's called the Hamiltonian operator on it. That's just math, or really the physics. So it does physics on the probability distributions of where the electrons are, and it spits out an energy. So the whole point of the Schrodinger equation, okay, is to associate an energy with a probability distribution of where the electrons are. I wish someone told me that when I was an undergrad taking PChem. No one ever told me that. I just got completely lost. My PChem classes were horrible. I won't tell you where I took them. You didn't mention it. I had a PChem class where the professor came into the class with the textbook, stood in front of the class, and read it aloud. Yeah. Okay, that's probably why I care about teaching. I don't want to be like that. Okay, but if you now have physics that allows you to associate the probability distribution where the electrons are with an energy, well, then you can optimize the positions of the electrons. You can change the probability distribution, see if the energy goes down. And you can keep doing that to find the ideal distribution of electrons around nuclei. And then if you want, you can change the nuclei, do it all again. That's how quantum mechanics work. Now you know quantum mechanics. Okay? So in a quantum chemical calculation, again, you have to guess at where the nuclei are. Those are the atomic coordinates. You have to give it the Hamiltonian operator, which I won't talk about. That's give it the physics. And you have to give it the set of atomic orbitals it can use. And what you get out are, again, new atomic coordinates, an energy, and a wave function. So a picture of where the electrons are likely to be. And any good quantum chemist will tell you, if you have the wave function, you can know anything you want about the molecule. You can turn the wave function into lots of different kinds of things that chemists care about. And I don't want to dwell on what they are. Okay? So that's what we do. So to contrast the two, classical mechanics is empirical. It depends on parameters that people like us put in to the force field that we use. Quantum mechanics is what's called ab initio, which means from first principles. You don't need to put in any parameters. It's just going to use the physics and figure everything out. That comes at a cost. Okay? Quantum mechanics is much, much, much slower than classical mechanics. So it's always a trade-off between accuracy and time you're willing to wait for an answer. Again, in classical mechanics, you ignore the electrons entirely. Everything's based on the positions of the nuclei. But in quantum mechanics, it's all about the electrons, and then you deal with the nuclei secondarily. Okay? Everyone understand everything about computational quantum chemistry? Okay, I don't care if you remember any of this. Well, I'd like you to remember something. I don't know what. Anything from what I just told you. So the goal is to get a picture like this. All right? So this picture is a plot, the vertical axis of which is energy, which is also color-coded. And then the other two dimensions of the plot are something about structure, or as a chemist, we might call them degrees of freedom of the molecule. Something you can change about the molecule. A length of a bond, an angle between three that defines where three atoms are, something like that. Okay. And there are a lot more than 2 degrees of freedom for any molecule. It depends on the number of atoms in a molecule. But as humans, we're stuck with being able to visualize only a small number of dimensions. And you're after a plot like this, which shows how the energy changes as you change different aspects of the structure of the molecule. And there are certain points on this plot that we care about. There are the low points in the plot. Those are called minima. So for a chemical reaction, one of those is the reactant, and another one is the product. Okay, and then there's a pathway that connects the reactants to the products. And the highest point on the lowest energy pathway that connects reactants to products is called the transition state, or the transition structure. So the usual analogy that's made is you want to get from the reactant to the product, it's like climbing over a mountain, and you take the mountain pass rather than going way up here over this high point. Okay? So you want the lowest energy pathway to get to the products. So I'm in the business of kind of defining this path, this black line, and the points along this path. Okay, here's just an inspirational quote. This is old. I'll read it to you. Every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. You can remember that if you don't like anything I'm talking about. This is old, outdated. I like to read this quote every so often to get me fired up. Okay, so why should you care? How and why do we use these techniques? Well, we use these techniques to, if we know the structure of a reactant and the structure of a transition state, then we know how much energy we need to get past the transition state and get to the product. So we know the energy barrier for a reaction. And that energy barrier is related to how fast the reaction goes. The bigger the barrier, the slower the reaction. So we can predict rates of reactions. And that's super important if you want to figure out, if you want to design a catalyst for a reaction to make a reaction go faster, you need to be able to predict the rates. So I'm just going to give you one example of that has to do with trees. So Titus mentioned natural products briefly in his introduction. So natural products are molecules that are made in nature. Okay, I'm actually teaching a natural products class right now to undergrads. These are some trees on the Davis campus, but these trees are making many, many interesting molecules for many purposes, and we as humans are taking them from trees and using them for other purposes. So for example, if you've ever heard of Taxol or paclitaxel, it's a famous anti-cancer drug that's produced by the Pacific yew plant. Okay, so that's something that the plant is producing for some purpose, but we found that that's useful to humans, and then we're taking that and using it. So a large part of my research over the years has been to try to understand how these molecules are made in their biological setting. So I'll give you one example of that, and then I want to show you how you do that if you're blind. Okay, I want to show you how hard that kind of problem is, and then how you can possibly make that accessible. Okay, so the kinds of molecules that are my favorites are called terpenes. So if you've never taken organic chemistry, you haven't learned yet that organic chemists are somewhat lazy. I'm an organic chemist. So we abbreviate everything. So these are pictures of molecules where we've not written atomic symbols for anything. So every line in these pictures is supposed to be a bond between carbon atoms. So at the ends of every line segment, there's a carbon atom with some number of hydrogens that you should know if you're an organic chemist. That's the way we do it. Nothing like making it hard for outsiders to understand what we're talking about. Okay? I think what you can see, at least, is that these structures look pretty complicated. But in nature, they're made from things that are less complicated. These are the precursors in nature. So this group on the right of each of these is called a diphosphate group. So if you've heard of ADP, like ADP and ATP, the DP in ADP is diphosphate. That's the same group here. Okay? And this diphosphate group is connected to just repeating units. So the biosynthesis of these molecules is interesting. You make repeating units and you stick them onto this diphosphate group, and then there's one enzyme that'll turn this simple thing into this complicated thing, or this simple thing into this complicated thing. There are hundreds of different complicated things that have the same number of carbons and hydrogens as this one, and they all have this same starting material, the same reactant. And there's a different enzyme to make each of them, but they all come from the same starting material. So we're trying to understand how you could take the same starting material and turn it into one of these hundreds of different things. And that is all what's called carbocation chemistry. So a carbocation is a carbon with a plus charge on it. Okay, so what happens is this diphosphate group, which has negative charges, leaves a positive charge on the carbon, and we try to understand how you go from something simple like this to something complex like that. Okay, so here's a specific example. So here's a simple thing. I've drawn it in a complicated looking shape, but it's just that same repeating unit over and over again. I abbreviated the diphosphate group, but that's what we do. Okay. this is one enzyme turns it into this molecule, copalodiphosphate, and another enzyme then turns it into this molecule, miltiridiene. So I want to tell you just about this step here. And I thought, since most of you don't know chemistry, I would pick the most complicated thing I've ever done to show you, okay? All right, so this is a project that came to my attention, was brought to my attention by Ruben Peters, who's one of my collaborators. He's at Iowa State. And miltiridiene, the molecule that we care about, is actually transformed in nature further into molecules called tanchinones, which come from a Chinese sage plant called tanchen. So that's where tanchinone comes from. And these molecules have lots of interesting biological properties, but we're trying to understand how the key core skeleton of these molecules is put together. All right. So we start with what's called a mechanistic proposal for how this happens. And so there's a molecule that's the starting material, and then it's proposed by someone in the literature that this molecule is turned into that carbocation, and that carbocation is turned into this carbocation, and so on and so on. Okay. And I won't dwell on the details. My former student, Young, looked at this molecule, and what we did is we built each of these structures, and we did quantum chemistry on them. We refined their geometries, got their energies, connected up their paths through transition states, and worked out how you could get from connect the reactants to the products. And we did that, and we got a really complicated picture. All I want you to take from this picture is that it's complicated. All right. And these are energy numbers. There were 3 different ones because we do that with different flavors of quantum mechanics to make sure that our results are not biased. That's not the type of bias we're usually talking about here, but there's bias in quantum chemistry too. And so this is a complicated picture. I do want you to notice that the word bifurcation shows up a bunch of times here. I'll explain what that means. So normally, for chemical reactions, you have a reactant, and if you can make 2 products, say product 1 and product 2, there is a separate pathway to each of them. So there's the green pathway that goes through a transition state. That's the symbol for a transition state, because even TS for transition state needs to be abbreviated down to a symbol. So the reactant can go through a transition state to product 1, or it can go through a separate transition state to product 2. Okay. And computational quantum chemistry for years has been in the business of calculating these 2 transition state structures. And from the energy difference between them, you can predict what the major product is and how much of it should be formed. The lower energy transition state will lead to the major product. There are 2 mountain passes. It's easier to get over the lower one. Okay? But not all reactions follow that model. This is what we teach undergrads and grad students. But once in a while, you have a different situation where the reactant goes to a transition state structure, which has another word with it. You don't need to worry about that word. And as you fall down in energy from that transition state structure, the pathway actually splits in 2. So from this first transition state structure, you can get to 2 different products. So that's a problem for me, because I no longer have 2 competing transition structures to compare. I have 1 transition structure that leads to 2 products. That's called a post-transition state bifurcation. A bifurcation is a split in 2, happens after a transition state, post-transition state bifurcation. So let me explain this in a way that you'll probably remember. This is my PhD advisor a long time ago. His name is Ken Hauk from UCLA. So I did know about California before I came here, so that's why I knew I wanted to come back. He's riding some creature. He's not sure what it was. He thinks it was a so-called Highland cow, and I have his permission to use this picture. So imagine that you're at the back of this cow, okay? And you want to get to the front legs, and you have to go over my PhD advisor. So the highest point you have to go over is his head. So that's the transition state, okay? And as you fall down the front of him, if you just fall straight down, you're going to hit the cow. So you have to pick a side. You have to go to the left or to the right to go down one or the other leg. That's a bifurcation, okay? A chemical reaction is very much like that, okay? So like that, let me try again. Okay, here's a playground in Davis. If you know this particular slide, then you know the neighborhood I live in, okay? This is my son a few years ago going down a slide, but he climbed up to the top of this slide, and there was a bifurcation in front of him. He had a choice. Do I go to the left or do I go to the right? Right? Molecules have a choice. They go over a transition state. If there are 2 ways down in energy, they're going to have to pick one way down in energy to go to one product or the other. So that led us to doing calculations that are called ab initio molecular dynamics. So that means that not only do we look at the pathways on the surface, we allow the molecules to have the energy that they would actually have at a reasonable temperature and vibrate accordingly. And the way that you choose which pathway you take depends on how the molecule is vibrating. So if my son were running towards this bifurcation, right, and he were swinging from side to side, which way he was leaning when he hit the bifurcation would probably determine which side of the slide he went down. It's the same thing for a molecule. If a molecule is vibrating in a way that pulls it towards the right, it'll go down the right path. If it's vibrating towards the left, it'll go down the left path. And so we can model that for molecules, and that's what we do. So here's an energy surface where there's a reactant in the back. You go over a transition state, and now there are two different ways down. And when we do the modeling, some molecules go to one product and some go to the other. And we can do that 100, 200 times and just count how often do you get one product, how often do you get the other, and predict what the major product will be. And then try to understand why one is favored over the other. So that's what we spend a lot of our time doing now. Okay. In this complicated picture I showed you before, there wasn't just one bifurcation, there were multiple bifurcations. So that's why I say this is the most complicated thing I've ever done, because you get a transition state, as you fall down the pathway splits, but then the pathways that split also split. And so you can actually get one transition state structure that leads to, say, 9 different products. Now, I see a couple chemists in the room. I'm assuming most of you aren't chemists. That is weird. I grew up in Boston. I wanted to say that's weird. Okay, it slips out when I talk to my parents. That is very, very strange. Okay, and this is a biological reaction. So I'm going to show you how we understand what's going on there. And now I'm going to show you a picture that's going to simplify everything for you. Got it? Okay. I mean, that was a joke. I know. Not all my jokes land. Okay. Let me explain this picture for you. So this is like a polar plot. Okay. As you go from the center of this plot to the outside in any direction, the energy goes down. Okay. As you rotate around this plot, you're changing what's called the dihedral angle. That measures how this carbon unit changes. So if I have 2 carbon-carbon bonds connected by another carbon-carbon bond, I can rotate like this. Okay? And so there's what's called a dihedral angle. So if they're lined up, that dihedral angle is 0. If they're opposite, that's 180. If there might be 90. Okay? So for every structure I showed you in that complicated picture, I can put a little dot on this plot that corresponds to that dihedral angle, and then which contour line, which circle on the plot corresponds to the energy. And then I can start running dynamic trajectories, they're called, from the transition state, which is the purple dot, and see where they go. Well, if I do that, I should say, if we do that, actually you get trajectories that lead to 12 different products. So this is a problem that an enzyme has to face. The molecule itself, no enzyme in this modeling, the molecule itself could make 12 different products. So how does the enzyme only make 1? So that's really the question, which is not the question that people usually ask about this enzyme. But what we find is that, and this is the reason we plotted it this way, what we find is that the most common products come from only a very small change in that dihedral angle from where it started. First, let me just show you a video to wake you up. So here's one trajectory. Okay, so here's a structure. So white or hydrogen, green or carbon. Here's an arrow pointing at the bond around which you're going to rotate. So my students and I run these trajectories, and then we sit around and we watch these movies and try to figure out what's going on. So when I hit go, you're going to see this hydrogen is going to jump, and then the molecule is going to rotate slowly around this. And everything is going to be wiggling and jiggling. So here we go. There it goes. The hydrogen jumped. Okay, and then ultimately, this carbon-carbon bond here is going to break, and you're going to make a new carbon-carbon bond over there. Okay. So this is what we get out of these sorts of simulations. We can see how everything moves as you go from transition state to product. Okay? And we can do this hundreds of times. And when we do that, in this case we did it 183 times, and 91 of those times, so half, you made a product which actually is the product that's made in nature. To me, that is mind-blowing. No enzyme here, okay? If you just look at the energetics of the small molecule, you could get 9 or 12 different products. But if you account for how the molecule wants to vibrate with no enzyme around, half the time it just wants to make the product that's made in nature, which tells you something about nature. Nature must, I say must. Nature is likely taking advantage of this preference, okay? And this comes from a very small dihedral angle change. Almost half the time, it makes one other product that has not been observed in nature, which is also very interesting. And so now we've changed the question. First we changed the question to, hey, you could make 12 different products. How is nature making only one of those? Then we rewrote the question again to, actually, if you take account for the dynamics, nature's only making 2. And so now the question is, how does nature just not make this one? And that's what we're still trying to figure out now, okay? So that is an example of the kind of research that we do. That's what I said. And then what keeps me up at night is when I sit around thinking about how does this play into the evolution of enzymes and organisms, right? So people think about dynamics of proteins, how proteins wiggle and jiggle. Most people don't think about the dynamics of the small molecule substrates for the proteins themselves. And so that's kind of what we're in the business of doing. We're actually spend most of our time not answering questions, but rewriting the questions. Okay, so now the question is, how would you do this kind of thing if you can't see? So, and I can't answer that in full, but I'm going to tell you some of the progress we've made. All right. So I do want to point out that I'm here not just as a representative of myself and my research group and Davis, but I'm also a member of the American Chemical Society's Committee on Chemists with Disabilities, whose vision statement is making chemistry accessible to all. And I want to tell you a bit about a former student of mine named Hobie Wedler, who some of you might have heard of. Hobie has got a lot of press over the years, all of it completely justified. Okay, he's still in the Petaluma area if you want to meet him. And Hobie he's born completely blind, so he's been completely blind since birth. But he's always liked science. But he was told from a young age that maybe he shouldn't pursue science because it's not suitable for a blind person. Okay, how can he be in the chemistry lab, for example? Okay, which is a horrible thing. So I met Hobie when he was an undergrad here at Davis. And here, I'll go to the next slide. First, I'll give you my philosophy on the things that we did together. We did a lot of things together, but my outlook has always been, as a scientist, I'm a problem solver. Okay? So if you can just explain the problem to me, I can try to help you solve it. And so a lot of the issues in this world, and I mean that in a small sense and a big sense, are actually just understanding what the problem is. And so Hobie and I worked well together because he was great at explaining the problems in a way that I could get them. And we had all these discussions where when we could both wrap our heads around the problems, he explaining to me problems that affected students that were blind, and me explaining to him problems in chemistry. It went both ways. Once we could understand the problems, then we could tackle those problems together. Okay, we were able to work towards solutions. So we worked on a lot of things. This is a paper that, if you're interested, that summarizes a lot of things we did together. Yes, this picture involves blind and blindfolded people doing wood turning on a lathe. And there's a reason for that we can talk about later if you want. We also dealt with issues like service animals in chemistry labs, things like that. We had for a while a committee in our department called the Accessibility Committee, which is now part of a bigger Diversity, Equity, Inclusion, and Accessibility Committee in the chemistry department. Okay, so how did I meet Hobie? Well, Hobie was an undergrad and he was taking a lot of chemistry classes. He started out as a triple major in chemistry, math, so that's why I see some mathematicians nodding, and history. So I believe he ultimately graduated undergrad only as a double major, and I think math was demoted to a minor, sorry. He only had so much time. Actually, his history focus was conspiracy theory, which is very appropriate also. So he's taking chemistry classes, and at some point he talked to my colleague Jared Shaw about how he really liked chemistry, but he didn't think he could do research. And Jared knew me, and he said, hey, wait, you should go talk to Dean, because Dean does computational chemistry. You wouldn't have to be in the wet lab. And then Jared had this vision of, we could maybe make a robot that would take balls and sticks. You know, organic chemists like model kits like this. We're all like Lego kids. Where you take balls and sticks for your computed structure, and the robot could assemble them, and this. And Hobie came to talk to me, and I'm like, well, we'll just get a 3D printer and print them out. That's what we should do. So that's how Hobie and I got connected, and he started doing research with me as an undergrad, and then he stayed on for his PhD. I also want to acknowledge Sarah Cohen, who was Hobie's partner in crime and assistant throughout his time here at Davis. She didn't know chemistry when she started. By the end of her time with Hobie, she was taking chemistry classes by herself because chemistry is awesome. Okay, just throw that out there. Okay. So this is one of the things we tackled. How could Hobie run calculations? Well, to run a calculation, remember, you have to guess at what the structure of the molecule looks like. What are the atomic coordinates? And there's a direct payoff for how long your calculation is going to take to finish and whether or not you're going to get a reasonable answer based on your chemical intuition. You know, if you have a good idea of what it should look like, your calculation is going to be faster because you're going to be closer to the end point when you start. So computational chemistry is not just automated, right? You still need people with chemical intuition to make it work. So what Hobie would do, what we decided is he could think of a molecule that he wanted to calculate, and then he would write something called a SMILES string. So a SMILES string is a text-based way to indicate which atoms are connected to which. These are used in, for example, the pharmaceutical company to keep track of libraries of molecules. So he could write a SMILES string for any molecule. Most organic chemists don't do that. They draw a picture of a molecule like this and in a program, then they click a button and it makes a SMILES string. But he could write them by hand. Anything text-based was fine for him. So he would write a SMILES string. They look kind of like this. And then there was an existing software that would convert a SMILES string into a reasonable guess at what a structure would look like. Do that in a text file. We'd modify that text file so we could use it with the program, send it off to the program, and then we would get our optimized structure, say, of a transition state or a reactant or a product, and then we'd have to get it in a form where Hobie could use it. So what we decided to do there was to 3D print it. So here's an example of that. So here's a research paper that Hobie did with me, and this is actually my wife, who's a faculty member in food science, so who has studied olive oil and also studies now avocado oil. And so we were looking at a reaction relevant to olive oil processing. And so Hobie built these structures and computed them, and then we 3D printed them. So here's a picture of our what's now an old expensive 3D printer. You could get something, we paid like 50, well, we didn't, NSF paid like $50K for this. You could get something better than this for a couple $1,000s now. This is why we glommed on to 3D printing, because we knew at the time that it would be like laser printing. You know, it was going to come way down in cost and everyone was going to have one. And at the end, you could print out a model. This one is in color. This printer doesn't print in color. Hobie doesn't care about color. But we had a student in the lab who just wanted to paint everything, so she just painted everything. These are Hobie's hands. The thing about printing these is it's not trivial. There was no program that would take atomic coordinates and turn it into a ball and stick model. So we developed that with some colleagues in the Netherlands, and ultimately what we were able to do was take those coordinates, make a ball and stick model out of them, where every different atom type had different texture. So carbons were smooth, oxygens had one kind of bumps on them, nitrogens had a different kind of bumps. And then you'll see here, on the sticks that correspond to the bonds, there's a flat panel with a condensed form of Braille on it, which actually gives you the bond length that you got from the calculation. So this bond is 1.53 angstroms long, so Hobie could read that with his fingers. Okay? And how big of a molecule do you want to print out? Well, I like little tiny models, but that doesn't work for Hobie. You have to think about the resolution of someone's fingers when you do this. And so you get a model like this. You know, if you've ever done 3D printing, this is the classic sort of plastic-based version where you print things on fixtures and then you have to remove the fixtures. At the end of that, you get a model, and this is the resolution of Hobie's fingers, which is a typical size for a lot of organic model kits, the ones we make the students buy when they take into organic chemistry here. Okay, and then he can read this just by moving his fingers around. We learned that he didn't need the textures on the atoms because he could tell just by what was connected to what atom type it was. But reading off the Braille labels was super useful, and we thought about putting a lot of other information onto these models, but then Hobie graduated, and I'll tell you what he went off to do. So he wrote a dissertation that was a mix of not necessarily straightforward, but classic chemical research and his research on making chemistry accessible. So his dissertation was a mix of those two things. Here's a picture when he left my group. We used to do group selfies before COVID. And here he is at graduation, where he gave a graduation speech. His favorite part of that was when we were, rehearsing. You go if you've ever been on a stage party for graduation, you come the day before and you rehearse. And so Hobie was setting up. Does anyone know what this is? This clear thing here? This little square that's clear? That's a teleprompter. And so the guy asked Hobie, "Is that teleprompter working for you?" And Hobie can't see anything. So he's like, "Oh yeah, it's great. It's great, man." So Hobie's that kind of guy. Here we are posing for a graduation picture. So Hobie went from maybe you shouldn't even do science to getting a PhD in chemistry. And then originally he was going to be a chemistry teacher, but he was sort of bit by the entrepreneurial bug. And so, I support my students in whatever they want to do. It's a loss for chemistry, but Hobie's very happy. If you want to see what he's doing, go to hobiewedler.com. He consults with a ton of companies on that care about different sorts of sensory inputs, so everything from cell phone companies to all different things. He also sells his own spice blend. If you go to Amazon, you can get a Hobie's Spices. That's not the official name. I forget what it is. So he's pretty awesome. So I just want to mention some of the remaining challenges in this area. So I told you that Hobie could write a smile string to indicate the connectivity of a molecule, but that is really not sufficient, because any given molecule could have a bunch of different shapes, right? And that program that we use to convert the smile string into an input file will only give you one of those shapes. And if Hobie wanted a different one, he still had to work with a sighted person. And so we think this is a completely solvable problem. We just haven't done it yet. Hobie left, the pandemic hit. If anyone here in this room wants to do this, come talk to me. We should be able to do this with 3D scanning. It shouldn't be a big problem. We can just print out 3D print model pieces that we want, and then we should be able to scan them in and then shrink our scan down to atomic size. It should be no problem to then allow someone who can't see to use their chemical intuition to their advantage in creating a more meaningful input file for this type of chemistry question. Also, reading the chemical literature is actually one of the biggest problems. Okay, text is no problem, but is anyone in this room? I know there's a couple people in the back who probably read an organic chemistry paper before. If anyone hasn't, this is what organic chemistry papers look like. Okay, a figure like this is not accessible to someone who cannot see, for a lot of reasons. And the committee I'm on with American Chemical Society is still pushing for alt text, which is any figure will have text with it that describes what's in the figure, but that won't solve this problem. There's so much information in this figure, you need a 10-page paper to explain it. So this is very much an unsolved problem. Some people, including us, have dabbled a little bit with image extraction and blowing up images and printing them kind of on embossed paper, but this is still an area where people who can't see need help for complicated structures like this. And not just in chemistry, that's just the specific area that I work in. And the bigger problem is getting resources to help people who sort of are small markets. So I've talked a lot to Hobie about this. He has like an input device that in Braille that he can input things into. I said, Hobie, that looks like something from the 1960s. And he said, yeah, but people don't update those and make them modern because they're not going to make money off that. There aren't enough blind people to make a lot of money off of improving that device. So iPhones, for example, have been great, although they've gotten worse over time. The accessibility has actually decreased over time for people with vision problems, according to Hobie. So how do you get resources for small markets? Well, Hobie is very practical, and we had what we called Hobie's rule. His rule was anything we develop for him has to be useful to people who can see as well. And everything I told you, 3D printing of molecules, 3D scanning that we want to develop, would be completely useful and is completely useful to someone who can see. I mean, I love holding models of my molecules, and I get a lot out of that beyond looking at a computer screen. And that is a very practical consideration. I'll just show you one example of that from someone else, not me, who developed a sign language for organic chemistry. This is the SLICE project, Sign Language Incorporation in Chemistry Education. I don't believe anyone on campus here is using this, but there have been some new signs developed for various aspects of organic chemistry. And in this, that's mentioned in this Journal of Chemical Education paper, but there was a recent Nature Reviews chemistry paper that pointed out that when students were surveyed, when students who could hear were surveyed, 60% mentioned that they used these signs or thought about them when they were answering questions on an exam, even though they weren't deaf or hard of hearing. And also, anecdotally, that this was extremely helpful for students for whom English was not their first language, right? So a lot of times, Hobie's rule is not a requirement, and often benefiting people who weren't in the target audience is an unanticipated outcome, but that is one way to get the resources we need. So I'm both upbeat and cynical, okay? But in a realistic sense, this is a powerful strategy in what I would call our less than perfect world. So if you can appeal to a broader base, that's a way to get what you need for the smaller community as well. Okay, so the take-home messages from this part, we talk a lot about diversity, equity, inclusion. American Chemical Society adds respect to that and R. Some people add belonging. There's a lot of other letters added to that. But I want to argue that we shouldn't forget people with disabilities as well. We shouldn't forget that small groups need resources. I think, Hobie was a big proponent of advocating for yourself and advocating for others, as am I. And I think we should all seek out possibilities. In other words, focus on what you can do. So some of the challenges that Hobie described to me, we couldn't accomplish, but we should all just keep chipping away towards the greater good, I think. And everyone should consider getting involved. I'm not telling you have to get involved, but I'm going to put in a plug for getting involved when you can. And these are some of the other things that I'm involved in that I'm passionate about. And so if you like the dynamic stuff I talked about, we set up a website for common organic reactions to use when you're teaching organic chemistry. For example, I mentioned the American Chemical Society committee that I'm on. If you like the terpene work I mentioned, me and another professor on campus, Philip Zerba, and Ruben Peters, who I mentioned, my collaborator, are bringing an international meeting called TerpNet. Yes, there's a meeting specifically about that class of natural products to campus this summer. Come, join us, okay? I don't know why it advertises us with these pictures. This is not what the campus looks like, but we're trying to suck in people, okay? I'm a participant in what's called the Alliance for Diversity in Science and Engineering. That's an organization that started in chemistry, but is broader than that, and it was active, and then it kind of, our local chapter was active and then kind of went away, and now it's being rebuilt in chemistry, and we're hoping to expand that. So if you don't know about that and you want to, let me know. I'm sure it should partner with other groups. I'm one of the faculty advisors for that. At one point, I made that show up. We had an exhibit in the Arboretum, so we partnered with the Arboretum. This is Philip Zerba here. This is one of my former students, where we put up informational signage and we attached 3D printed molecules with Braille to that signage, and we used to give tours around the Arboretum. So we care about getting this out to the public as well. And then for anyone who's a faculty member, if you're here, I probably don't need to say this to you, but if you're a future faculty member, our job consists of research, teaching, and service. And you're going to run into a lot of faculty members who complain about service and having to do service, and they shouldn't, okay? So my unsolicited advice to you is embrace service and seek out service that's meaningful to you. So my particular service that I put a lot of time into is graduate education. So I've been on graduate council here and currently on the system-wide version of graduate council. Service can be a wonderful thing if you choose the right kind of of service. So consider doing something, anything. Don't just focus on only your research. Okay, so to leave you, I just leave you with this question. Think about what a chemist looks like, what a chemist is, what chemistry research is. You can all answer that question for yourself. And I'll just thank Hobie, who I mentioned, and Young, who did the calculations that I mentioned in the beginning part. And I'll thank my group as a whole. This is our group symbol. This, you can't tell, this is a stylized post-transition state bifurcation. I made that symbol. I'm very proud of it, so don't say anything negative about it. Jason and Tim were other people who worked with Hobie. Gert and Valère were the chemists in the Netherlands who helped us with 3D printing. My department and college have been very supportive of this work with Hobie, as has NSF, who's also funded our computational chemistry research, and I already mentioned the ACS Chemists with Disabilities Committee. Thank you all for listening and tolerating some chemistry, and I'm happy to take any questions. Thanks a lot. Titus, there's a question right behind you.
Anybody? No, just kidding. Here you go.
Thank you. Great presentation. And actually, it's good. You are speaking about this because when people think about academic diversity, there's always the racial ethnic component.
Yep.
And we have we have also other angles of disability, gender, transgender, disability, socioeconomic. So I think
yes.
To be a more inclusive institution, we need to consider all of that. So I commend you for that great work. But disabilities is a difficult one for us to measure or to see because a lot of the disabilities are unseen, right? A lot of us may have a disability and we don't want people to know about it, right?
Correct.
We don't want to be defined by them. So it is kind of difficult to tell, when someone has that. I'm thinking about, let's say, people with dyslexia, right?
Yes.
So, I wonder if you could comment about how we can be more effective in teaching or create an environment that also allows them to thrive.
Right.
When we cannot recognize all these abilities that we have in the classroom.
Yeah, so that's a great point. So, right. So, not only shouldn't you, but you're not allowed to ask someone about their disabilities, right? And it's up to each of us if we have a disability, whether or not we want to share it. So, Hobie was a champion for saying what you need, and people will usually help you get what you need. But not everyone is willing to do that. So that is a real issue. So to be as inclusive as possible, we should try to anticipate that, but it's hard, right? So I don't have a great solution to that, but I can tell you, for example, that whenever Hobie took a class, it caused the teachers who taught him to be better teachers. That's a subjective assessment on my part. But what I mean by that is they spoke more slowly, they spoke more clearly. I'm including myself in that. Instead of, that molecule over there did this thing, they were a lot more explicit, right, in what they were saying. And anecdotally, everyone else in the class benefited from that. So I think there's a lot to learn from that we could incorporate into how we teach. And I think I continue to incorporate those things, and I hope that I haven't sort of fallen back on the laziness, in a sense, that I had before. I'm not 100% certain. It's always hard to look at yourself from the outside. Although I record my lectures, I should go watch them. So I think a lot of it is just actively thinking about who might be in your classroom, and if they were, what would help. I don't have any great answers. I personally believe, and I did, for a long time I was strongly against recording lectures and posting them, but I've completely flip-flopped on that, and now I record all my lectures and I post them, and I personally believe that is something that can help a lot of people. It can be misused by other people, but everyone's an adult and they can choose to use the resources we give them, how we provide them, and that's not enough to make me not want to provide that as a resource, and that's my personal choice, and I have my reasons for doing that. Davis is, being on grad council and things, there are rules about live streaming classes and things, but it's completely legit to record your classes and post them after the fact. There's no restriction on that. So that's one thing I do to improve accessibility to material that I think benefits everyone. But yeah, I mean, I think that I'm not sure what the global answer is, other than to actually actively give some thought to who might be in your classroom, right? Whether it's a physical disability, whether it's a socioeconomic issue, in how that plays out in the policies that you've set for your class on your syllabus and things. Yeah. It's a great question that it doesn't have a simple answer.
Yeah, I really like when you hear faculty talk about accommodations,
Yes.
they view it as a sort of zero sum. I'm making this accommodation, and the energy that I have to put into it means that it's going to be taken away from something else. And I think your point, like, yeah, but you're becoming a better teacher and serving more people. It's not just
Yes.
targeted at one person. It's a much broader.
Yeah, so I've been involved in a lot of discussions. I was chair of graduate council, vice chair and chair of graduate council during COVID, and when everyone was suddenly doing online instruction. And it's a legitimate thing that it's a lot more work to do that, especially when you're doing it for the first time, right? And I'm very conscious of the burden on faculty, but I always think first about students, and try to weigh that, like what is reasonable to do that will benefit students, right? And so, I personally don't think I would ever want to give my class completely online, and that's just my preference. I think there has to be a good pedagogical reason, an argument for that. I'll tell you that talking to Hobie after COVID, for him, he said Zoom was an equalizer for him. When he's in a room of people, it's much harder for him to be engaged and participate in the discussion. But on Zoom, it was much better for him. And then I feel like as soon as the pandemic was over, I'm doing my hated air quotes, which I despise, everyone's like, well, great, we don't have to use Zoom anymore. And I'm like, wait a minute. Why don't we, it's kind of like what you're saying, why don't we learn from what we just went through and take the positive things out of that? It was also very frustrating for people in Hobie's community who for years asked for accommodations of getting classes recorded and told, no, we can't do that. And then suddenly when everyone else outside of his community needed it, we did it in the span of a couple weeks, right? So those are the kind of things that I think about. Yeah.
Any questions? Okay, let's start here and then in the back.
And make sure you get that guy in the back. He's a chemist.
Well, I'm a mathematician, but I'm going to try to ask you a question in chemistry. Maybe it's meaningful.
Nice.
So when you were talking about these bifurcation cases, where you go to this side of the slide or to the other side of the slide, so you get all these different configurations. So my question is, are there ways to predict the largest number of possible configurations? I mean, under this framework, it seemed to me that it will be some kind of finite space of possibilities. And
I'm not sure I fully understand your question, but as far as I know, aside from very highly symmetrical cases, most of which are not relevant to the real world, there's only ever a bifurcation, right? And then to get to more products, the bifurcation has to split into another bifurcation over and over again. And that could be as many as you could. It all depends on the molecule and what degrees of freedom could be involved. To my knowledge, the one I showed you is the most products you can get from a single transition state that's yet been described. But I don't see why there couldn't, in principle, be more. Yeah. Most of the time, it's one bifurcation and people trying to figure out how, which side is preferred and why. Yeah. It's a good question.
So thank you for your talk. It's very 233-like style.
233 is my graduate physical organic chemistry
favorite.
class that this gentleman had to take in the past.
I'm glad, yeah.
He's not in my lab, by the way, just so you know.
Yeah, I'm nice, but you're my favorite. So, so the thing is, what do you think about GTP3 in helping? No, I mean,
Yes.
well, before AI enslaved humanities, I think that GTP is really useful. We try to use some GTP in the lab to help us to summarize things, etc. I think. So you mentioned that it's difficult for those people cannot see to read the paper, and what I can envision is we can feed the paper to GTP maybe 4, and then ask the GTP, okay, can you print out the scheme 3 molecules for the reactions?
Mm-hmm. I think that's a great question and a great suggestion. So I think we're going to talk more about this kind of thing in the panel, but I'll just say my general attitude on AI in general and machine learning in chemistry is a giant thing now is that we shouldn't do it just for the sake of doing it. There has to be a purpose, and there has to be, and the purpose has to be it's going to be better or faster than something that we already know how to do. Okay, so students in my group who want to do that, I'm like, sure, but you get to tell me why. As far as things like ChatGTP, you know, I don't really worry about being enslaved by the machines, and I'm in the group that feels like we should stop worrying that it's going to ruin everything and think about, like you said, how we could use it to help people. And so I really appreciate your suggestion. I feel like, you know, when a lot of people have said this, but you know, when the calculator was invented, that's it. Math is done, right? Or when Google was invented, that's it, right? You know, so this is another disruptive thing, but we should make sure it's not misused, but we should focus on all the good things we can do with it. And your suggestion is one that I haven't thought about, but maybe there's some good possibilities there. So thanks. Yes.
I was just wondering, for this molecule, you said that it was like really unusual with all these possible products it could create. Is that something that like, do you think we're going to start finding more molecules that are like this?
Yeah.
Is this, I guess I'm asking you to speculate, or is this because our computational tools have gotten good enough to find all the reactants that could?
That is a great question. So, so when I started studying bifurcations, I started by accident because I found one related to this one, okay, that was in the context of a natural products project. And I knew of a couple of examples that were out there that were known. So we weren't the first person to find a bifurcation. And then we found this one, and then we found one in a completely different reaction that involved a rhodium catalyzed reaction that synthetic chemists use. And then we found one somewhere else. And then other people were finding them all over the place. There aren't many examples of multiple bifurcations in a row, but they're coming out. So I think it's a small percentage of reactions, but it's a lot. There's a lot of reactions. So there are a lot that have always been there, but been overlooked because, as you said, the computational techniques to characterize them didn't previously exist, nor did the mindset to recognize them. That when I first started talking about this, I would go give seminars in chemistry departments, and people would tell me that's not possible. You can't have two products from the same transition state. And I would say, well, let me try to explain it in a different way, right? Or I'd throw up that picture of my son or something, because we weren't taught that because the dogma was that's just not how it is, right? So it's both the understanding has improved, and so people are now able to look at results from that viewpoint and know how to recognize it, and also the computational tools have developed so that you can characterize it. It's both. So yes, there are a lot more out there. Again, it's not every reaction, but there are a lot out there. So thank you for your question. I know it's time to eat.
Yeah, it's time to eat. So thank you. Let's give our speaker another round of applause. I feel like I should confess that I have never taken a chemistry course in my life, which got me into a little bit of trouble when I moved into molecular biology, but that's a different conversation. So now we're going to move to eat lunch, and I believe it's being served out by the posters. So again, down the hallway, out to the right, look for the poster boards. You are welcome to bring your food back in here if you want to eat it at a sitting down and not in the sun, but you can also stay out there. And then at 12:45, I'll come back here and remind anybody that's crept back in here that we're going to start the poster session, which will go until about 2 o'clock. One quick note: if you want to leave your stuff here, there's going to always be somebody in this room. So during lunch, so feel free to leave your bags and your laptops and stuff here, and hopefully they'll still be, and there will be someone here keeping track of them while we're out there. I'm gonna lead by example and just leave my panoply of Apple devices all in one place, except for my phone, which I can't live without. So let's have a great lunch. 12:45 for the poster session, and back here at 2 o'clock ish for our third talk. Thank you.